Here's our first example on capacitors. The plates of an air-filled parallel plate capacitor are 1 centimeter apart. How big would the plates have to be for the capacitor to have a capacitance of 1 microfarad? Dielectric breakdown in air occurs when the electric field is greater than 3 megavolts per meter. What is the maximum charge that can be placed on the 1 microfarad capacitor? How big would the capacitor have to be if we put a slab of ceramic between the plates? And they're giving us a dielectric constant for the ceramic of 173, which is a very high value. And do you think that the ceramic-filled capacitor can carry as much charge as the air-filled capacitor? Here's a diagram of a situation with the parallel plate air-filled capacitor. I'm going to assume that the plates are circular, which would make their area pi r squared. And the formula for the capacitance of a parallel plate capacitor is epsilon naught multiplied by the area of the plates and divided by the space between them. Combining those two equations, we get that the capacitance will be epsilon naught multiplied by pi r squared divided by d. And since the question is about the size of the plates, we are going to try to solve for the radius. We get that the radius is equal to the square root of the capacitance multiplied by the distance between the plates divided by epsilon and multiplied by pi, which would be 10 to the negative 6 multiplied by 10 to the negative 2 divided by 8.85, 10 to the negative 12 multiplied by pi. That's a little unusual, so a quick unit check tells us that 10 to the negative 6 is in farads, the distance between the plates is in meters, and then the 8.85 times 10 to the negative 12 is in farads per meters. So under the square root, we have meters squared, and our units are okay. We get that the radius of the plates should be 19 meters. Now let's see about the maximum charge on the plates. We know that for 2 plates, the electric field is given by sigma, the charge per unit of area, divided by epsilon naught. We know that the maximum electric field that air can withstand before ionizing and sparking is 3 million volts per meter. And that would make the charge per unit of area equal to the maximum electric field multiplied by epsilon naught. Charge per unit of area is charge divided by area, and so we can replace the sigma with Q over A in the equation that we have. And the maximum charge on the capacitor is given by the maximum electric field multiplied by epsilon naught multiplied by the area of the plates. So 3 times 10 to the 6 volts per meter multiplied by 8.85 10 to the negative 12 farads per meter multiplied by pi multiplied by 19 squared. We get that the maximum charge on the capacitor is 3.01 10 to the negative 12 coulombs, or 30.1 millicoulombs. Now let's see how big the plates would have to be if we put ceramic between them. Once again, assuming circular plates, the area will be pi r squared. The value for the capacitance will be the dielectric constant multiplied by epsilon naught multiplied by the area of the plates and divided by the distance between them. And we combine those two equations once again, solve for r and plug the numbers in. We get that r is equal to the square root of 1 microfarad multiplied by 1 centimeter divided by 173 multiplied by 8.85 10 to the negative 12 multiplied by pi, and that gives us a radius of 1.44 meters. So we can have capacitor plates that are a lot smaller when we put a dielectric between plates. Now to determine if the smaller capacitor with ceramic in the middle can handle as much charge as the much bigger air-filled capacitor. Well, the answer on that depends on the maximum electric field that the ceramic can withstand before dielectric breakdown, before it sparks. So we use again that sigma is equal to the charge over area, and that the electric field between two plates is the charge per unit area divided by epsilon naught. Combining those two equations, we get that the electric field is equal to the charge divided by the area and multiplied by epsilon naught. And plugging the numbers in, the 30.1 millicoulombs divided by pi multiplied by the radius of the new capacitor, 1.44 squared, multiplied by 8.85 10 to the negative 12 farad per meter, is 5.22 times 10 to the 8 volts per meter. 522 megavolts per meter. So if this ceramic can withstand an electric field greater than 5.22 10 to the 8 volts per meter before sparking, it really can carry more charge than the air-filled capacitor. However, that is unlikely because that is a very large electric field. So most likely, the ceramic capacitor is smaller, but it can't carry as much charge as the air-filled capacitor. Here's my problem solution on 2 pages, and spread the joy of physics.